All right, in our day 4 lesson, what we're going to be doing is kind of combining what we did in days 1, 2, and 3 and write explicit rules for each of these sequences. Now remember, recursive is when we would write it as one term is dependent on the previous. A sub n is equal to, a sub n minus 1 plus 3, or a sub n is equal to 4 times a sub n minus 1. Those are recursive rules because you need the previous term to get the next one. Whereas explicit rules allow you to get the exact term you want without going through the steps of finding everything previous. So if I wanted the 7th term of a sequence, I could just substitute 7 in for n instead of having to find the 6th, 5th, 4th, 3rd, 2nd term like we would with recursive. So when we are writing these explicit rules, we got to remember the formulas from the day 2 and day 3 notes. Now we're also throwing some neither sequences here, and for neither sequences, we must look for a pattern. Think about the position of the number, like the n value. Look for perfect squares and perfect cubes. So we're going to write an explicit rule for this. And again, I always check to see, is it something that I'm adding to get the next term or multiplying to get the next term. So here I see plus 3 plus 5 plus 7. Now when you have a pattern like this where you're adding 3, then adding 5, then adding 7, you're adding 2 to what you're adding. 3 plus 2 is 5, 5 plus 2 is 7. When that happens, that is a clue for it being a quadratic or a squared term. And if we look at these values, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. So my explicit rule is going to be a sub n equals n squared, because I'm squaring whatever position that I'm trying to find. So like I said, if I wanted to find the 7th term, I could just substitute 7 in for n and get 49 instead of having to work my way up from 1. Okay, so now for letter B, I see that it's 2 plus 2 is 4, plus 2 is 6, plus 2 is 8. So that tells me it's arithmetic, and I'm adding 2 each time. Now remember, for arithmetic sequences, you have to find that b value or that y-intercept. Now you could set up the formula, or one of the shortcuts that we could do is say, okay, if this is my first term, and this is my second, third, and fourth term, my b value is going to be what happened before here. Like, what was this term right there that I added 2 to get 0? Or sorry, 2 to get 2. That would be 0. So our b value is 0. So, for arithmetic, and maybe we should write these up here. Arithmetic and geometric, what the explicit formulas look like. For arithmetic, a sub n equals d times n plus b. That was the formula from day 2, which is kind of like mx plus b. And then for geometric, it was a sub n equals a sub 1, the first term, times the r value, or the rate, what we're multiplying each term by, raised to the n minus 1 power. So now going back down here, our b value was 0, and since we're adding 2, that is the d, or the common difference. So a sub n is equal to 2n, and we don't need to add plus 0. Right now with letter C, we have 3, negative 3, 9, negative 27, positive 81. When you see alternating signs like that, that is a clue that you're multiplying by a negative number. because a negative times a negative gives you positive. So in this one, we're multiplying by -3 each time. So that means -3, this is the R value, or let's use lowercase like in the formula. And this right here, this is our first term. So we're going to use that formula from up here for geometric because we're multiplying each time. So our formula is going to be a sub n equals that first term, -3, times r, which is also -3, raised to the n minus 1 power. All right, letter D. We have a fraction here this time. The numerator is always 1. And the denominator is growing quickly, so we're not adding anything each time. So again, I'm thinking first term, second term, third term, fourth term. Well, I know that 2 to the third power is 8, 3 to the third power is 27, and 4 to the third power is 64. Oh, and this works too. 1 to the first power is 1. So our formula here is going to be a sub n equals 1 over n to the third power, or if you use negative exponents, n to the negative third power. Either one of those is okay. Most of us, and I'm perfectly happy with this, that's the most preferred one. So again, when you're not having a geometric or arithmetic sequence, you need to look for patterns, those perfect squares, those perfect cubes. All right, so now this team problem, I have +2, +2, +2. So this is arithmetic. So what happened before this? Well, this has got to be a 1 because 1 plus 2 gives you 3. So this is my B value, and this is my D value, and then I can use that formula. So a sub n is equal to D, which is 2, times n plus that B term, which is 1. Now, if you wanted to solve for B, one of the ways we did in the notes, substituting in a term, that's fine. This just may be a little bit quicker. All right, now with this one, I'm noticing that the denominator is the same thing we had up here, 1, 4, 9, 16. So this makes me think that, these are all perfect squares down here. And then it's really over 1. So the denominator is squared, but the numerator stays 1. So a sub n equals 1 over n squared. So now this last one here, so this last row here, I'm looking and I was like, okay, 0, 3, 8, 15, 24. So they're not perfect squares. Let's see, what are we adding each time? +3, +5, +7, +9. Okay, now remember what I said up here when we were adding, +3, +5, +7. I said, hey, if the number we're adding is increasing by 2, then that's a clue that it's going to be something squared. So look, I have +3, 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9. So I'm thinking that this has to do with something being squared, and all of these numbers are 1 less than these up here. Except we don't have 25 here, but we do have 24 down here. All these numbers are 1 less than the square. If this is 1 squared, 1 minus 1 is 0. 2 squared is 4, 4 minus 1 is 3. 3 squared is 9, 9 minus 1 is 8, and so on. So a sub n is going to be equal to n squared minus 1. And once we're all done with these, I'm going to go back and highlight which ones are arithmetic, geometric, and neither. Now, up here, the numerator starts at 2 and then goes 3, 4, 5, 6. So we're adding 1 each time. Okay, no big deal. The denominator, I start at 1 and I'm adding 2 each time. If you notice that, plus 1, plus 1, plus 1, plus 1. And then down here is plus 2, plus 2, plus 2, plus 2. So what is happening is that we have an arithmetic sequence in the numerator and an arithmetic sequence in the denominator. So what we'll do is we'll look at these separately. So what came before 2 if I'm adding 1 to get the next term? So it's going to be 1, because 1 plus 1 is 2. And then in the denominator, what came before this? Well, that had to be -1, because -1 plus 2 is +1. So our formula, the numerator is going to be, my d value is 1, so 1n, or just n, plus that 0 term, or the y-intercept, which is also 1, over, in the denominator, I'm adding 2 each time, so it's 2n, and then that 0 term, or the y-intercept, is -1. So by looking at this as a arithmetic over arithmetic, I could use those rules to get the rule as a whole. Now you might say, is this sequence as a whole arithmetic? No, it's not, because I'm not adding the same thing each time to get to the next term. I have 2 over 1, then I have 3 over 3, which is 1. Then I have 4 over 5. I'm not adding or subtracting the same thing to get the next term, so this is not arithmetic and it's not geometric. It's neither. However, you have an arithmetic sequence on top and on bottom. All right, now the last one, we have 9, then -6, then 4, then -8/3. Now, when I see this divided by 3 all of a sudden, that makes me think that something is being multiplied by something over 3, 1 over 3, 2 over 3, 4 over 3, or whatever. And one of the ways we can do this and see if there is a common ratio is dividing two adjacent terms. If I take this term and divide it by the first term, that's going to give me -2/3. Now, I want to make sure that this rule, that this R value applies to the whole sequence. So if I have 9 times -2/3, okay, I get -6. I want to times -2/3 again. Okay, that does give me +4. If I hit enter again, I do get -8/3. So this is the R value, -2/3. And then our first term, our ace of 1, is right here. So we're going to use the geometric sequence formula. Ace of n equals that first term, 9, times the R value, -2/3, raised to the n-1 power. So again, anytime your signs are alternating, that is a good indicator that it's geometric. And if you're not able to see the common ratio real quick, you can just divide two adjacent terms, and that should give you the R value. But you do want to make sure to check it like we did in the calculator. So this is geometric because we multiply by -2/3 each time. This is neither, because we're not adding or subtracting or multiplying or dividing the same thing to get the next term. This one is also neither, Because again, we're not adding the same value to get the next term. We're adding 3, then we're adding 5, then we're adding 7. This is also neither. Now, any of them that have an n raised to some power, that's going to be neither. Right here, we were adding 2 each time, so this is arithmetic. This one, again, we have that exponent 1 over n squared, so this is neither. Multiplying by -3 each time makes this geometric. Adding 2 each time, this is arithmetic. And then because we have n squared here, that is neither. So in my experience, students do really well when we focus on one sequence at a time, like arithmetic, then geometric, then neither. When things start to go a little bit south is when we're combining all of them like we do in this lesson. So just make sure you're remembering all the rules and trying things here and there to see which rule fits your pattern. So thanks for watching. Make sure to like this video and subscribe.